All right, so the first lesson in this new unit is on factors and multiples of whole numbers. All right, so yeah, so let's start off in the first example here. We want to write the prime factorization of 2,646. Okay, so first things we want to know is what is a factor. So a factor, factor is a number that divides without a remainder. Okay, so I'm sure you've heard of the word factor before, right? This is hopefully some review. All right, so factors are numbers that divide into a number without a remainder. All right, so I'm just going to break this one down. So 2,646. When you're asked to find the prime, write the prime factorization, what we want to do is we want to write 2,646 as a product of prime numbers, right? Or yeah, so prime numbers. That's why I call it prime factorization. All right, so the best way to do this is actually to start chopping up the 2,646 into like the product of two numbers. So for instance here, I think since it's an even number here, 2,646, I'm going to just write this as 2 times, or it's going to be 2 times, and then if I take 2,646, so just to avoid making a mistake, use a calculator. Okay, so if I take 2,646 and divide it by 2, that's equal to 1,323. Okay, so 2,646 is the same as 2 times 1,303. Now, obviously, we can't. There's no other number to divide into 2 except for 1 in itself. So this is a prime number, so we're going to leave the 2 alone on this side. However, the 1,323, I'm going to try to break it down even further. All right, so let's see here. Next thing you want to do is check if you can divide by 3. Okay, so you guys might actually not know this, but to check whether a number is divisible by 3, what we can actually do, and this is kind of a trick, is you can actually add the digits of the number together. So in this case, I'm going to take 1 plus 3 plus 2 plus 3, and I'm just going to add those digits together. So that's 4 plus 2 is 6 plus 3 is 9. Okay, so again, I got the 1,223. What I'm going to do here on the side here is just add up the digits. Now, when I add up the digits, if this number here, so notice it's a lot smaller than this number here, but if this number here, the sum is actually divisible by 3, that means the number itself is divisible by 3. All right, so that's a lot of mumbo jumbo, but it's kind of a neat trick. All right, so if you add up the digits, and when you find that sum, if this number is divisible by 3, that means that 1,323 is also divisible by 3. All right, so this 1,323, if I pull my calculator back up here, I'm just going to divide it by 3. And I shouldn't get a decimal, I should get a whole number, which I do. All right, so 441. Okay, so this is 3 times 441. Now I'm going to apply the same trick to the 4,441. I'm going to add those numbers together. That's 4 plus 4 is 8 plus 1 is 9, so I get 9 again. All right, so that means that 441 is divisible by 3. All right, so I'm going to take the 441, which is in my calculator, divide it by 3. That's 147. All right, so the 441 That's again is 3 times 147. All right. So see what I'm doing here? We're just kind of keeping breaking this down. The 147, 1 plus 4 is 5, plus 7 is 12. 12 is divisible by 3, so this number here is divisible by 3. Divide that by 3. I get 49. All right, so this is 3 times 49. All right, so what do I got now? 49, 4 plus 9 is 13. 13 is not divisible by 3, so 49 is not divisible by 3. However, if you think about your times table, right? 49 is the same as 7 times 7. So this 49, I can break it down to 7 and 7. All right, and now 7 is not divisible by any number. These are prime numbers. All right, so so we're done in terms of, this is called a factor tree. All right, is when you break this down. So what this means is that if I take these numbers that are off to the side here, the product of those numbers is the original number itself. All right, so in other words, 2,646 is going to equal 2 times 3 times 3 times 3. Right, I have 2, 3, 3, 3 times 7 times 7. All right, and if you, and this we can kind of simplify. So this is also equal to 2 times, instead of multiplication, I'm just going to write a dot. I have 3 3s, so that's the same as 3 to the power of 3. So in other words, that's 3 cubed. And as well, I have 2 7s here, so that's 7 squared. So this here is 2,646. All right, so you can kind of keep breaking it down, and then once you get just prime numbers there, those are your prime factors. So there you go. So if I took 2 times 3 cubed times 7 squared, maybe I'll just quickly show you on the calculator. All right, so if I take 2 3 times 3 times 3 times 7 times 7 equals, you can see that is equal to 2,646. All right, so yeah, so this is what they call prime factorization. All right, when you break down a certain number down to its prime factors. Cool. All right, so next up, we want to determine the greatest common factor of 126 and 144. All right, so greatest common factor is the largest number that divides into both numbers without the remainder. So yeah, so there's going to be a factor or a number that divides into both of these, 126 and 144, so that there's no remainder, and we want to find the biggest one, the biggest number that possibly does that. All right, so to do this, for like smaller numbers, right, so if these were like 2-digit numbers, you could probably just figure it out in your head, but since we're dealing with kind of bigger numbers here, it's not really evident. So there's a kind of a systematic way we can do this, and it does involve what we did in the previous example, which was a factor tree. All right, so the 126, I'm going to break this down. I'm going to write down the prime factorization. So this is the same as 2 times 63. Well, 63, I can break that down as 7 times 9. And 9, I can break down as 3 times 3. All right, so so for this first number here, 126, I'm going to write 126 is equal to 2 times 7 times 3 times 3, right? Or 3 squared. Now you do the same thing with 144. So if I break this one down, that's the same as 2 times 72. 72 I can write as 8 times 9. The 8 I can break down as 4 times 2. The 4 here I can break down as 2 times 2. And this 9 over here, all right, so these are all prime factors of the 8, 3 times 3. All right, so what that means is that 144 is equal to 2 times, all right, so I'm going to take this one, and I'm going to take the lowest number in each branch, so that's 2 here and 2 here. So 2 times 2 times 2. 2 times 2 times 2 times 3 times 3. All right, so actually, let me just write the 126. 126 prime factorization is 2 times 7 times 3 times 3. All right, so to find the lowest common multiple, once you've broken it down into the prime factorization, is basically you want to find the common prime factors that show up in both. Right? So, but you can only count them, like match them up 1 for 1. So this 2, I'm going to match up with this 2. There's no more 2s up here, so these 2s I'm not going to circle. However, I got a 3 here and a 3 here. So again, I'm matching this 3 with this 3, as well as this 3 with this 3. All right, so again, it's got to be a 1 for 1 match. So what that means now is the lowest, greatest common factor of the GCF going to be the product of these numbers. So in other words, 2 times 3 times 3. But you only count it once. All right, so 2 times 3 times 3 is 6 times 3, which is 18. Okay, so that means, so these are common, right? The 2 and the 2, 3 and 3, and 3 and 3. So once they match up, the greatest common factor is going to be the product of these. So 18 divides into 1 into 26, and 18 also divides into 144. So 126 divided by 18, 7. 144 divided by 18 is 8. Okay, so 18 does divide into both of these. All right, cool. So that's just a systematic way of getting the greatest common factor. Some of these you can probably just do in the head, the smaller numbers, but once they get a little bit bigger, you want to break them down. If you can't figure it out right away, you want to break them down into their prime factorizations and any common factors. The GCF is going to be the product of those ones. Cool. All right, next up. Now we're going to find the least common multiple of 28, 42, and 63. All right, so instead of a factor, multiples, actually the best way to explain multiples is, for instance, multiples of, start with 28, all right, the first number there. So it's going to be like 1 times 28. So the first multiple is obviously itself 28. Then 2 times 28 is 56. 3 times 28 is equal to 84, right? And so on. All right. So basically, what you'll notice too is to go from one to the next, basically you're just adding the number itself, right? So from 28 to 56, you're adding 28. 84, you add 28, and so on. All right. Now what we could do is we could start listing off the multiples of 28 and keep on going here. We can also list off the multiples of 42, and the multiples of 63, and then figure out the first one that shows up. The first one in the list that shows up is going to be the least common multiple. All right, but that could take time and so on. So what I'm going to do here is I'm actually going to show you the kind of like the more systematic way of doing this. All right, and yes, it does involve prime factorization again. Okay, so let's just do that. Let's find out the prime factors or prime factorization of each one of these numbers: 28, 42, and 63. All right, so 28, if I break that one down, That's 4 times 7. If I break down the 4, that's 2 times 2. Okay, so 28 is going to equal 2 times 2 times 7, which is the same as 2 squared times 7. Okay, so that's the first number. I'm going to do the same thing with 42. If I break down 42, that's what's that? 6 times 7. If I break down the 6, that's 3 times 2. So 42 is equal to 2 times 3 times 7. And the third number, 63, I break that one down, that's 7 times 9. And the 9 I could break down as 3 times 3. So therefore, 63 is equal to 3 times 3 times 7. All right. Now, why did I do that? All right, so the reason I did that is now the least common multiple is going to equal the product of the greatest power of each multiple. All right, so what does that mean? All right, so what you see here is that we've got the numbers that show up in our prime factorizations are 2, got a 2, 7, and a 3. So in this case, the lowest common multiple is going to equal 2, and the highest power of 2 that shows up, let's see, is right here, right? So I have 2 squared, but I have a single 2 here. But in my lowest common multiple, I want to count the highest power. So 2 squared. In terms of the 3, 63, I could write as 3 squared times 7. So the highest power of 3 that shows up in these ones here is 3 squared. And then the highest power of 7 is just 7 to the first power. So the lowest common multiple here is going to be 2 squared, which is 4. 4 times 3 squared, which is 9, times 7 is going to equal 36 times 7, which I'm not going to do in my head. Okay, so 4 times 9 times 7, 252. All right, so this is kind of like the most systematic approach of getting the lowest common multiple between these 3 numbers. All right, between 28, 42, and 63. All right, now I do have, I have some room here. So I'm just going to kind of show you that this is true using the other method, which is to kind of list them off, right? So 28, 56, 84, 28 times 4 is 112. 40. What's the next one? 168. 196. 224. All right, so hopefully you guys see what I'm doing here. 252. All right, so the answer I found here in the first method was 252. So I'm just going to stop here at the 28. This here, I'm just doing this to kind of show you that it's true, right? So multiples of 42, it's 42, 84, 126. I'm trying to do this in my head. 168. 2 is 210. and 252. All right. And then the last number there was 63. So I think it was 63. Yeah, 63. All right, so that's 63, 126, 189, 252. All right, so if you look at these lists and compare the lists, right, the number that shows up in common with all three of these is this 252. All right, so there's no number in beforehand that shows up in all three. All right, sure, 126 shows up here. However, it doesn't show up in this list here. Right, 168 shows up in these two, but doesn't show up in this one. All right, so the first number that shows up in the list for all three is 252, so that's your lowest common multiple. All right, but rather than writing them all out, you could do this, but it's a little bit more time consuming. I think it's actually a little bit more systematic if you do the prime factorization. Cool. All right, so next example. This time we got a bit of a kind of a word problem, but hopefully it'll make sense. All right. So what is the side length of the smallest square that could be tiled with rectangles that measure 16 by 40 centimeters? Okay, so to explain what the question's actually asking, it probably makes sense to draw a diagram. So basically we want to make a square. So that means length is equal to this length and so on. So all four sides are the same length. If we were to use rectangles that measure 16 by 40. All right, so inside here, I'm going to tile these with rectangles that are 16 by 40. So down this way as well. Okay. So we want to create what we want to do is we want to create a square though. All right. So so maybe or hopefully this kind of makes sense where in order to be a square, right, this length here, which we'll call x, must equal the same length here, which is also x. Right. So in other words, if you think about this, right, the question's basically just asking you what is the lowest common. Oops, sorry. Yeah, sorry. So what is the lowest common multiple, right, between 40 and 16? So in other words, basically what we want to do here is we want to find the lowest common multiple between 40 and 16. All right. Okay. So the LCM between 40 and 16, we could do the prime factorization, but these two numbers are fairly smaller. So I think it's going to be a little easier if I just list off the multiples of 40. 40, 80, 120, so on. And then for 16, I got 16, 32, 48, 64, 80. All right, and I could stop there because now 80 shows up in both, right? So the smallest possible square would be 80 centimeters by 80 centimeters. All right. Hopefully that makes sense, right? So if I was to tile this, I can put, I guess, five of these 16s down this side, and then I would put just two. Actually, two. Inaccurately do this, but I would put two across this way, right? Because then it would be 80 by 80. All right. So yeah. So basically, this question is just asking you what is the lowest common multiple between 40 and 16. All right. So such that this number. So if I put multiples of 40 across this way, multiples of 16 down this way, what's the smallest possible square, or when would these two sides be equal? It'd be 80 and 80. All right. Next up, what is the side length of the largest square that could be used to tile a rectangle that measures 8 centimeters by 36 centimeters? Okay, so this sounds familiar, or it sounds similar to the previous example, but it's actually kind of backwards. I'm gonna say backwards. So we want to create an 8 centimeter by 36 centimeter rectangle. Right? This is the final product. And so what we want to do is we want to use squares, right? Square tiles, such that so these are all the same length. Right? And so what's the largest square that we could possibly use? All right. So you probably figured this out, that in this case, since we want to find the largest, we want to find the greatest common factor between 8 and 36. All right. So greatest common factor, number that divides into 8 and 36. Well, 8 doesn't go into 36, but 4 does. Right? 4 goes into 36, 4 goes into 2. So GCF is going to equal 4, right? Because 4 divides into 8 and 36. So therefore, the answer is 4 by 4 centimeters. All right. And yeah, so hopefully that makes sense, right? So again, I kind of inaccurately drew this. So this time I'm going to actually erase these little red squares. Because I know what the answer is, right? So so it's going to be 4 centimeters by 4 centimeters. So I'm going to put two tiles down this way, and then perhaps 9. 5, 6, 7, 8. Oops. So guys, this out. All right, so these are, well, this doesn't look like a square right here, but anyways, they're supposed to be, right? And hopefully that makes sense, right? This is 4, that's 8. I can have, these are all 4s as well. Well, 9 4s is 36. So that's using 4 by 4 squares, we can make a rectangle that's 8 by 36. All right, guys, cool. So hopefully that makes sense. Yeah.